Yes, we can hear you, sir.
Yes.
Good morning,
Can you
sir.
hear me?
We are hearing you, Prof.
I can hear you, sir.
Thank you very much. Thank you very much, Dr. Bishop, and then the organizer of this workshop. It's my pleasure to be here this morning to give this introduction to quantum stochastic differential equation and inclusion. By way of introduction, the theory of stochastic equations has undergone a very rapid development since the emergence of Ito's work on stochastic integrals in 1940. So when we talk about Ito integral, that was the beginning of the stochastic integrals, and the need arose as a result of the fact that the classical integral, the Newtonian integrals, and calculus efficient when it comes to the use of random phenomena. And as a matter of fact, you cannot interpret into integrals in the form of Riemann integrals. So we know that the Riemann integrals, Riemann integrals, they are deficient when it comes to. Hello, can you hear me?
Yes, can hear you, sir.
Okay. So that is the background. And so Ito developed that stochastic equations of 1944. And let me also say that there have been some development, a number of developments when it comes to the use of stochastic integration. For example, the classical integrations deal with deal with real valued function, real value random function, random variables, random function. But we now have development in the area of what we call non-commutative quantum stochastic integration, which are actually development, on the classical Ito integral. So by way of introduction, let me say here, before we continue, that there are so many people in the literature that have worked on the development of integrations apart from this classical one with respect to Brownian motion. The classical Ito integration is with respect to Brownian motion as pioneered by Ito in 1944. Okay, so but we now have a situation where even though apart from Ito's work in 1944, we already have some development, generalized that are driven by some other kind of stochastic processes apart from Brownian motion. So we have Levy process driven integrals. We have driven by Poisson processes and all the rest of them. But as I said earlier, these integrations were, the concern classical real value function. Functions that are taking values in the real valued field that are random. So now this workshop of today, we are going to talk about the quantum integrals, and then the quantum integrals develop, concern what we call operators processes, operators valued functions, as are distinct from real value function that E2 and other people did with respect to the classical stochastic integrals. So when we talk about stochastic, the quantum processes or non-commutative stochastic analysis, we are talking operators about operators that are valued in infinite dimensional spaces. Okay, Now, as I said earlier on, just to motivate our listener, to motivate everyone, there are so many theories that have come, that we have already in the literature. So many theories of non-commutative stochastic integration. You know, we have the one developed by Brinett and White. We have what we call Ito-Clifford integration. We also have the one developed by Hodgson and Pastatarati in 1984. We also have the one developed by Ekagore and his school, much later on. And each theory of integration gives rise to a corresponding theory of differential equation. Each theory of integration, quantum stochastic integration, gives rise to corresponding theory of stochastic differential equation. Okay, and so, but this today we are going to dwell on what we call the Hodgson-Pastatarati school. The Hodgson-Pastatarati stochastic differential equation developed in 1984. With the references are there, I think references 59 or so. We have later at the end of this slide, at the end of this PowerPoint presentation. So it has been discovered in the literature that Hodgson and Pastatarati theory of stochastic differential equation sufficiently generalize the Ito integrals. Sufficiently to generalize Ito integrals. So there is a way where we recover Ito integrals or Ito differential equation from associated quantum stochastic differential equation of Pastatarati, Hodgson and Pastatarati. So I want everybody to get this one very clear by way of motivation, that Hodgson and Pastatarati integration, they gave rise to stochastic differential equation. Now, Hodgson and Pastatarati. In fact, it's a generalization of Ito integrals. And Pastatarati Ito integrals will have some benefits that are not derivable from the classical stochastic differential equation, especially when numerical simulation, numerical solution of classical stochastic differential equation. We have some benefits. In the case of to simulate what we call the random increment motion, the random implement of stochastic process equation, we just calculate as if you are calculating things with the classical numerical analysis of classical initial value problem. So that is the motivation for us. And again, we also have the motivation that apart from applications to wider field where Ito integrals it much more than that. For example, quantum stochastic differential equation applicable to they're applicable to open system. They're applicable to open system. They are applicable to problem from quantum field theory, quantum mechanics. They are also applicable to problem from measurement, what we call measurement theory. They are also applicable for problem from optics, quantum. That's what we call quantum optics. So we have a scope of application for quantum stochastic differential equations. Compare with the classical one. So, as I said earlier on, there are so many people that are work on generalization of Ito work in the form of quantum stochastic analysis. Sometimes we call it non-commutative Part in the field of non-commutative stochastic analysis. In his paper 33, 34, analytic inclusion. Inclusions are generalized cases of inclusion. Inclusion is just a generalized, just a special case. What you have is set valued, the right answer, that is the coefficients are Lipschitzian. They are Lipschitz. They certify a kind of Lipschitz that we are going to highlight later on. And then we also have some of his work also on hypermaximal monotone inclusion, that is where the coefficients certify the condition of being hypermaximal monotone in some sense that that will be made clear later on. And of course, we also have that dealt with evolution equation. So that is what he did in 1992, 96, up to 1996. And then let me also say here that his work general equation. And again, that work also generalized some classical equation. As I said, we can default 35 is to use which generalize the Ito calculus to give a wider field, a wider spectrum for the work. And I said the other one is the work of Ito, the equation of Ito can be recovered from in 33, 34, 35. In study quantum stochastic differential inclusion, very general condition, a very general problem arising from what a category did treats those the general conditions to special cases. We look for along with the condition and his paper under monotone. So use some partition of the interval of the time interval. In quantum calculus, we call the interval where the equation lie as time interval. Which is an interval in the real in the positive segment of the real number. Solution of two scale compare and prove give a conversion of sequence of solution approximating the same. That's what he did in the evolution paper that he did. In this workshop, we shall begin with general introduction in section 1, section 2, and structures, which set the foundation for subsequent section. In this section, we present results concerning the existence and uniqueness of solution of Lipschitzian quantum stochastic differential equation, and we establish equivalent form of such inclusion. Let me start here by saying that we are starting on equation, to make life easier for our people to follow us, and then we generalize later. And we're also going to start on equation that are Lipschitzian, that is equation where the coefficient satisfy the Lipschitz condition in our sense, in the sense of
Hello.
quadratic
What's your name, sir?
Yes. Hello?
When is the payment, sir?
Hello? This result are a summary of the result established in 33 for Lipschitzian quantum stochastic differential inclusion. They are specified with the case of Lipschitzian stochastic differential equation. So equation 1.1, as you can see from the screen, we consider quantum stochastic differential equation of the form ddt inner product of an element of the initial. I'm going to explain all this later on. So the quantum stochastic differential equations in the sense of Calgary publications of 1992 is of this form. We call it the equivalent form. Equivalent form. So we are going to have the general form following. So ddt inner products of those two conditions equals to P of t, X of t inner eta psi. These eta psi are elements of the dense subspace or the Fock space that we are going to introduce. So there's nothing to worry about. So we are going to define all the concepts clearly later on. Okay. So what we have, the right-hand side of equation 1.1, let me stay right from the beginning. The right-hand side of equation 1.1 is not of classical type. It's not of classical type. I will explain that, what that means later on. And you see that equation 1.1 is an equivalent form of the quantum stochastic differential equation given by 1.2. You can see dx of t is equal to e of t xt driven by half pi of t plus f of t driven by af of t, g of t driven by ag of t plus h of t. And x of t naught equal to s naught. So t belongs to the time interval. We are going to define what we mean by all this term. Equation 1.2, equation 1.2 is the equivalent of equation that we can consider as a Cauchy kind of problem. A Cauchy problem, just like you have the y dt is equal to f of t y, but it's not of the same. It's not of the same general form as the Cauchy problem. So we are going to establish that in equation 1.1, the map. Okay, let me talk about the map that apply at the right-hand side. The map is a set, what we call is in the space of circular form. So circular form, in fact, we use a circular form a lot, and then the integrator that appears in equation 1.2, that is the integrator if f, that is you have a sub f, a sub f dagger plus, and then half pi. So they are called stochastic process, called the annihilation, creation, and gauge operator processes with values in the locally convex space L theta. So we are going to define that locally convex space L theta where these integrators take values. Where the integrator takes values. So as I said the other time, we are working in infinite dimensional space, unlike the classical theory of Ito that work in finite dimensional Euclidean space. To work in infinite dimensional locally convex space, whose we have a family of same there. So we are going to define that L there, named by H. So we are just name annihilation, creation, and gauge operator processes. Let me also say here that these processes, they are related to the processes, the annihilation, creation, particularly in their paper of 1984. So it's related. So we just say, you know, they are related. Let me just say it that way. So it's not a new thing. And then we are going to define how they are related to the annihilation, creation, gauge operators of quantum field theory. So these operators, the integrators, they come from quantum field theory that Houston and Patrati didn't use in their paper of 1984. and that is why it's so wide. It's so applicable. So the coefficient AFGH in equation 1.2, our condition is there is that it may belong to the space L2 log I cross A theta. We are going to define that one very shortly. So, but it's mimic the usual locally, usual L2 spaces that we know, but it's local. They're locally co-integrable. So AFGH, they are supposed to be locally co-integrable on the space I cross A tilde, where A tilde is an infinite dimensional locally convex space. Okay, so next we demonstrate that classical stochastic equation, as I said earlier on, of Ito type is a special case of quantum stochastic differential equation. This is very important for beginners to understand, and that is why I said it earlier on that what we are doing generalizes what is known before in classical stochastic differential equation of Ito type. As I said earlier on, we have so many kind of stochastic differential equation. The one for Ito type is the one that by Brownian motion. So what we call, those of us that are not familiar with it, you can read it up. Brownian motion, there are special cases of stochastic processes that satisfy certain condition. They satisfy certain condition concerning their increment and concerning the mean of Brownian motion. So a classical stochastic differential equation has the form dxt equals txt dt plus b of t dq of t. So that is how it's the form 1.4, where A and B, where the noise of fluctuating can kill the classical Brownian motion. So sometimes we call it Wiener process. It's the same thing as Wiener process when we talk of Brownian motion. Okay. So, and then equation 1.4 is understood. Equation 1.4 is just the symbolic form of writing the classical stochastic differential equation, just in the symbolic form. But in the it's understood as equation 1.5. So equation 1.4 is an abbreviated form of the integral equation. So we actually understand equation 1.4 as an integral equation of the form 1.5. Okay, where A and B are Brownian functional. So we call them Brownian functional because they are adapted to the filtration. There's something we call filtration associated with Brownian motion. So the coefficient A and B for equation 1.5 to have meaning must be adapted. That's what we call adaptedness. We're going to talk about that one also later on. To the filtration generated by Brownian motion. And again, let me also say that A of X, A and B, they are real valued function, random function. They are real valued. They are not operator value, unlike the quantum cases that are operator values that lies in infinite dimensional locally convex space. So A and B, they lie in finite dimensional Euclidean space. They are random function, and then the first integral is the usual, the best integral. Sometimes it's a Riemann integral, it could be a Riemann integral, but in general, it's the best integral. And the second integral is the Ito integral developed in 1944 by Ito that we have been talking about. So the second integrals, Ito integrals, the first integrals can be understood in Riemann, the best integral in general, or Riemann Sujit integral, or Riemann integral. But let me also say one thing about the Ito integral of arising the second integral in equation 1.5. The second integral in equation 1.5, for it to exist, B, the coefficient, the integrand, must satisfy some condition. And that is why we say that A and B must be Brownian functional. They must be Brownian functional. Okay? And then K of X, Brownian motion. Okay? So the references are given there that we can check. So the Ito integral cannot be, as I said earlier, cannot be interpreted as an ordinary Riemann-Sujit integral, since Q is not differentiable in the ordinary sense. So you remember that the theory of Riemann-Sujits, that for Riemann-Stieltjes integrals to exist, the driving function must be integrable. Must be differentiable, in ordinary sense. But K of S, Brownian motion, is well known that Brownian motion is not differentiable in the ordinary sense. And therefore, the integrals, the Ito integrals arising 1.5 cannot be interpreted as Riemann-Stieltjes integrals. In fact, that is one of the motivation for the work of Ito in 1944. Now, the quantum stochastic differential equation arising from quantum theory, as I said, the latter may be regarded as a theory of non-commutative probability in which observables are represented by, in general, non-commuting self-adjoint linear operators acting on the dense domain of some Hilbert space. So we are going to talk more very shortly because when we talk of quantum calculus, quantum probability, non-commutative probability, which is also quantum probability, it deals with what we call observable, which are represented by non-commuting self-adjoint linear operators acting on some domain of some Hilbert space. So the Hilbert space that we are going to talk about, they are what we call Fock space. And then we have a subspace or Fock space that is dense. So our observable, the operators, they are going to be densely defined on the Hilbert space, which is Fock space, which is Boson-Fock space, as developed by Hudson and Pafferati in 1984. Okay, now quantum stochastic differential equation in the Fock space stochastic calculus developed by Hudson and Pafferati has the form 1.6. You can see that x of t equals to x plus all of that, where we have talked about the coefficient E, F, G, H, satisfying some condition. They are L2 lock on I cross L tilde. They are L2 locked, that is, they are square integrable, locally square integrable on the space I cross A tilde, where I is the time interval, cross A tilde, which is the locally convex space, infinite dimensional, that I talked about earlier on. So the quantum stochastic differential equation in the Fock space stochastic calculus can be written in the as follows. Let me say that differential from 1.7 is just symbolic. We actually understand it in the form of 1.6. And that integral, we only have one integral there. That integral, T naught T, that cover everything, E, F, G, H, they are just integrals developed by Hudson and Pafferati in 1984. And for 1.6 to have meaning, EFGH must also satisfy required condition. 1.6 to must satisfy required condition. Okay, so let everybody know that what we are written here, we are talking about integral equation 1.6, which is written in differential form. Differential equation is just notation, but actually it's in integral form of the form 1.6. So the integral in 1.6, the Hudson Pafferati Boson stochastic developing an integrator AFGH dagger have pi third value processes called the creation, annihilation, creation, and gate processes respectively for FG prime belonging to some function space. Let me say here that as we are going to see shortly, AF, that F associated with that A, the integrator, G associated with that integrator A plus, and prime integrated with associated with the integrator hat. They are also functions. They are also functions, and they must belong to certain function space for the integrator to have meaning. For the integrator to have meaning. So in the first space stochastic calculus, the processes AF A sub F of T, A sub G plus T and ST appearing in 1.6 belong to a locally convex topological space L tilde of operators which are densely defined on a linear subspace E of the Fock space spanned by the exponential pointer. We have what we call exponential vectors we have a source space or the Fock space. Fock space on its own right is an Hilbert space. So we have the Fock space there, and then we have a source, a dense source space, which we call the space of exponential vectors. And this space of exponential vectors form is the central of the calculus of Hudson and Pazzoratti that was developed in 1984. Okay. So for FG in L2 dagger, so again, we also have this space of L2 dagger R plus, and pi in L infinity lock B dagger R plus. We are going to define all of this very shortly. F and G are co-integrable function that are taking value in some space. Dagger, a fixed Hilbert space. Dagger, we have defined on R plus, that is defined on the positive segment of the real number line. And then we also have phi, which is also locally integrable. No, locally you have L infinity measurable with values in B dagger. That B dagger is the space of the bounded functionals on Hilbert space dagger. So, and it's also defined on R plus. So we are going to give the specific definition, the definition as time goes on, where dagger is a fixed Hilbert space, and B of dagger is the space of bounded endomorphism, all linear map on dagger that are bounded, So, you also know that it's also a Hilbert space if dagger is Hilbert. So the space of bounded linear endomorphism of dagger is also Hilbert. So the coefficient EFGH appearing in equation 1.6 are mapped from T naught T cross A tilde into A tilde, so that they lie in L2 lock T naught T cross A. This is what I call I cross A tilde the other time. So there's no confusion about it. It's the same thing. So if we consider the special case, okay, so this is how we recover the E2 from quantum calculus. So if we consider the special case where dagger is a complex number, the field of complex number is also a Hilbert space. So what we call it tree, it can be anything, space. But if we specify dagger G of T, identically phi of T, identically equal to 0 for all T, define on what we call this, that dagger there is talking about Fock space, determined by the space L2C. That is L2C is it is based on square integrable function that are defined on with values in the complex field. Square integrable, but know that. So we can also write A, because G and F are A F equals to A, and the key of T plus A dagger of T. So arithmetic is recoverable as by the sum of annihilations and which come from quantum field theory. So Brownian motion is the sum of A of T and A dagger T, where F and G are 1, identically equal to 1, and phi they are 0. Phi of T is 0 for all T. So you can say that this is just a special case. It is just a special case of the Fock space, the general theory. So we have that. So it can be shown that been developed in the Husserl and Paternotte paper that K of T equals to A of T plus A of T, A plus of T is equivalent to Brownian motion. So we have literature along that line by using the commutative, what we call the commutative relation, satisfied by the process A of T and A plus of T. The operator K of T are self-adjoint operators, adapted and mutually commutative. So the process K of T may therefore be regarded as forming a classical stochastic process, which has been shown to be a Brownian motion by using the mathematics of second quantization. There's something we call mathematics of second quantization that allows us to show that K of T, which is the sum of the creation and annihilation operators of quantum field theory, is equivalent to the Brownian motion. So this work that have been done, you know, we have it already. You can see the literature there. So people that are interested, you can read it. You can look for those references, 57, 59, 93, 110, and you can read it up. So these are the work that have already been done, you know, which we are building on in this quantum stochastic theory. So there's something we also call the vacuum vector in E, that is vacuum vector in the space of exponential vectors, which is a dense subspace of the Fock space, E. So we have what we call cyclic for K of T. That is repeated action of K of T on it in the total set of vectors in the Fock generated by L2 with values in the complex field over R plus. So we have what we call cyclic total set space, total in our sense. The Fock space generated by the L2 space into omega FW. You can see in the theory of for A and B, the coefficients of Vito calculus to make sense, they must belong to L2. FW, which is the probability space over which the classical Brownian motions is defined. So omega FW, omega is a set, and the W is it's a function. It's a set function on F. Hello.
You can speak on, Prof.
Okay. So I was talking on vacuum vectors in the space of exponential vector, which is contained in the Fock space, gamma L2C. Then we'll talk about the fact that the Fock space can be realized as L2. Because in the space of classical stochastic differential equation, L2 spaces are very crucial for the integral, the Ito integral to exist, to make meaning. The coefficient must be L2 over the Wiener space, omega, call it F and W. Okay, now we are talking about the realization of our stochastic calculus from the calculus of Husserl and Paternotte that was developed in 1984. So that was what I was talking about. And so, and I was given situation where we can realize them, realize Q of T as a sum of the annulators and creation operator when F and G are identically equal to 1 and the phi of T is 0, and that gamma become a complex space. And so the Fock space generated by L2C is now L2 over the Wiener space. So that is what we said. What you can see that the vacuum vector is very crucial in this realization, because it's very important for us to understand this realization because of the fact that we are doing Ito stochastic calculus. Okay. So, and we said the other time that K of T becomes the operator multiplication by canonical Brownian motion. Okay. So we now use the drift and diffusion coefficient A and B appearing in the Ito equation 1.5 to write as follows. So our F of T that appears in the quantum analog cannot be written as A of X of T, comma dots, where dot there is coming from Brownian motion. No, dot there is coming from the space, sample space, omega. You know, we are talking about Wiener process. We have sample space, omega, and call it F, which is sigma algebra of subsets of omega, and of course W, which is Wiener process. So for us now to realize our F, so we take our F to be the coefficient of the coefficients coming from Ito equation as AT, S of T dot, H of T dot equal to B of T, S of T, where F and H are non-anticipating functional. Non-anticipating Brownian functional. Anticipating Brownian functional that satisfies certain condition. There's certain condition, so we have what we call the condition of non-anticipating Brownian functional. So if you have that, then we also demand that for every T positive, the integrals of A of F of X square is finite. That is a mathematical expectation. So what we have there under this integral is mathematical expectation of E of F of X dot all squared integral is finite. And then mathematical expectation, the integral of mathematical expectation of H of X dot squared integral is also finite, where E is the expectation function with respect to the Wiener space. Okay, so the mathematical expectation. So these are the kind of condition over which the function will exist. The integral will exist. Now, as multiplication operator value process, where F is F of T and H equals to H of T, satisfy the integral, that is the norm. You know, we are now in our Fock space. We are now in our Fock space, our locally convex space. What we have here is the seminorm. So we now require everything to. As a matter of fact, the mathematical expectation in the classical equation now become what do we call it? Now become inner products. You now become inner products with respect to eta psi, which we have there. Square of them inner products. That is the seminorm. H, the topology of our A theta. So I'm going to, this is just a general view for you to see how it works in the realization of the Ito realizations of quantum calculus. So here now, we now take our alpha and beta. Alpha and beta, they are also function, a bounded function, which are purely imaginary function in L2C. so that eta is exponential of alpha, psi is exponential of beta, exponential vectors in the Fock space. So exponential vectors in the Fock space, they have this form. They have eta is E of alpha, beta, psi is E of, where alpha and beta are bounded purely imaginary function. So when we demand that a bounded purely imaginary function, it is to comply with the requirements of Ito integral with respect to quantum calculus. So constantly the quantum stochastic integral of f and h against the creation and annihilation operator, and the best measure is defined, and so we can write. So we can now write Ito equation in this form, in the form 1.8. In the form 1.8, we now write Ito equation in the form 1.8, which is s of t dot equals to all of that we have at the right hand side, where we now replace our e by b, and then h, our e by b and our h by a. Okay, we can see that it just makes some substitution, and so we recover Ito stochastic differential equation. I said earlier, where K of t is the evaluation of Brownian part at time t. So we have what we call Brownian part. That is, what is Brownian part is just Brownian motion as a function of t at any time. So it's a function of t, Brownian part. We call it evaluation of Brownian part at time t. Okay, so that is our winner process. So this work is deep, but I'm just giving you the overview so that the people that are interested, and so they can do more work along this line. There are many open problems that people are not really dealt with in this area, but one needs to be at the top of the materials. You know, you have to know them deep before you can begin to contribution in this area. Okay. So we now have a quantum stochastic differential equation now. Okay, you know, so much with introduction, we have this now. In the theory of classical, the numerical solution of stochastic differential equation is important. As a matter of fact, I can come to this one later on, you know, but let's move to how the A tilde, that in infinite dimensional space, being generated. Okay. Let's move to the way infinite dimensional space have been generated. So I've just put all this material together so that somebody can sit down and understand. Let's go to fundamental concepts and structures. It's very important for you to appreciate what we have been talking about before now. Okay? So fundamental concept and structure. So it's very important for you now to appreciate what we are saying. So how do we form the locally complex space? How is it? What does it look like? How does it look like? Why do we apply our inner products and our seminum in certain space, in certain way? So notation, so fundamental concept and structure. I hope you are hearing me. So fundamental concept and structure. Let D be an inner product space. So everybody know what an inner product space is. An inner product space is a space over which inner product is defined, or sometimes we call it scalar product. It's closed under the operations of a scalar product, you know. And as a matter of fact, Hilbert space is first of all an inner product space. So when every Cauchy sequence now converges in the inner product space, then we say it is Hilbert. Okay, the completion of D. So let D be an inner product space and H the completion of D. There's something we call the completion of an inner product space. An inner product space is not complete. But when we now so there's a process in analysis where we do completions of an incomplete inner product space. Okay? So every inner product space has a completion. So that's what we are saying. Every inner product space has a completion. So when we now use H as the completions of D, and we denote by L dagger DH the set of all X that map D to H. H is the completions of D, and then X is a map that take D to H, so that X is linear map satisfying domain of X star adjoint. The domain of the adjoint of X contain D, where X star is the operator adjoint of X. So I want us to know this one because this is very crucial to our calculus, the calculus of Hausen and partiality, very crucial. So we are talking about L dagger DH are the set of all map whose domain, whose the domain of the adjoint contain D. It contain D. So this one is a technical requirement for the theory of Hausen and partiality to be valid. So this requirement is a requirement associated with the theory of Hausen and partiality and the formulations of their integration, the stochastic integrals in 1984. So we are looking for all X so that when you take the domain of the adjoint of that operator, it contains the inner product space D. So we remark that this is a linear space under usual notion of addition and scalar multiplication. We can show you that is a linear space. That is, when you take any two operators in L plus DH, the sum is also there. The scalar product is also there. That is, the sum of any two operators from L plus DH also has the domain of the adjoint of that sum containing D. Okay, so and they are linear. So it's also that's well known as from elementary functions. So we can show that is a linear space. Now the next definition deals with the Fock space itself. The Fock space itself. Okay, so the Fock space itself. So we want now to go on to define our L tilde. So let H be a Hilbert space, and the Boson-Fock space gamma H. I've been using that symbol before now. Determined by H is an Hilbert space direct sum. Gamma H is the direct sum of this nature. When you take the direct sum from n from 0 to infinity of H to power, call it n. Where when you take n equal to 0, H to power, call it n is just the complex field. And Hn is the subspace of the n-fold Hilbert tensor product of H with itself. So when you take Hilbert space tensor product of H with itself n time, we have what we call there. So we call it symmetric tensors. So the tensor product space is very crucial to the theory of Hausen and partiality that we have adopted. And then you also find out that there's a lot of literature on Boson-Fock space, symmetric Fock space, and then in the theory of symmetric Fock space, you have the theory of exponential vector. So the next one define what we mean by exponential vector. If each f is h, an element of the form E of f equals to direct sum n factorial to power minus half tensor of f with itself n time. As you can see that f is an element of H, Hilbert. So you have that kind of that kind of composition. So we call it an exponential vector or coherent vector in the Fock space. Here, the product f to 0 is just 1. Yeah, that's notation. And then f tensor itself n time, the n-fold tensor product of f with itself. So the element E0 in gamma is called the vacuum vector. I've talked about vacuum vectors earlier on in this talk. Okay, so and then we have a remark here. You can see that what I'm doing here is that you have to lay foundation for the tensor product, for the exponential subspace of the Fock space. And we know that this the next one give us a remark, the properties of exponential vectors. The properties of exponential vectors. It's well known that the exponential vectors and the Boson-Fock space enjoy the following properties. You can see that So these are results that's been established long time in the literature. So let E be the span. That is, we are talking about the linear span of the set of exponential vectors as F belong to H. F belong to H Hilbert space. Then E, call it E, is dense in gamma H. That is, when we take the linear span, that is the set of all linear combinations of the exponential vectors, EF. So the first result is saying that that result is dense in gamma H. So, and the second one is saying that for every two elements in H, we have the inner product of E of F, call it E of G, is just equal to inner product. It's going to be exponential, the inner product of F and G. So these are very important, very interesting results that I find the application in the theory of Hopf and productivity integration. Okay, so for F and G in H, we have that. I notice that this inner product we are talking about is talking about inner product space, because the Fock space is a Hilbert space. So there is inner product there. So the Fock space, and then the inner product at the right left is the inner product of the Fock space, whereas the inner product at the right is the inner product of H. You can see the relationship, the inner products in H. Because F and G belong to H, we take the exponential of the inner product of F and G. Whereas the inner product of E of F and E of G is inner products of the Fock space. So the set A of F is linear independent in gamma H. So we have linearly independent set, which is also dense. Okay, you have the set A of F, linearly independent. E, the span, the linear span, the one that is dense. So if H is Hilbert space, direct sum, H equal to H1 plus H2, then the Fock space exists as, you can see this also, this interesting result, that if we can factorize the Hilbert space into the sum of two Hilbert spaces, then the Fock space generated or determined by H is also equal to the Fock space, the product of the Fock space generated by H1 and H2. So, and for arbitrary F1 in H1, F2 in H1, an exponential vector in gamma H is given by E of F, you can see that. So the exponential vectors in the E of F1, F2 is just equal to that. So since the exponential vector are linearly independent, an operator with domain E is well defined. It's very important. An operator with domain E. And that is why in the theory of Hopf and productivity, we resist ourselves, first of all, to domain, that is the linear span of the exponential vector, which is dense. By density, it means that when you take the closure of E, you are going to get the whole space. The closure of E equals to the whole space, that's density. Meaning that you can take any elements of the Fock space, and then if you have any element of the first space, you can have a sequence of elements of the exponential vectors, the domain E, that converge to it in the topologies of gamma H, the topologies of the Fock space. So it's also a very important result that I've found application in the theory of stochastic differential equation. So in what followed, D is some inner product space, and then with R as its completion, and gamma is on fixed Hilbert space. So for each T in R plot, we write, we have been using this symbol before, so we now define it formally now. We define it formally now. So for each T in R plot, we write L2 dagger R plus, respectively L2 dagger 0T, respectively L2 dagger T infinity. We have close at the left, open at the right, for the Hilbert spaces of square integrable gamma valued maps on R plus, the first one for R plus, respectively for OT, respectively for T infinity. Okay, you can see that the definition there for the Hilbert spaces of square integrable gamma valued map. Gamma is a fixed Hilbert space. Square integrable means that when you take the values of any element in L2 in gamma, and you take the norm, you integrate square, and then it's finite over that space. So the non-commutative stochastic process, which we shall discuss, are densely defined linear operators on R cross gamma L2 plus, and the inner product of this superspace will be denoted by that, and it's known by this symbol. Therefore, for each T positive, it is well known that the Hilbert space L2 gamma can be decomposed into a direct sum of L2 gamma R plus equals to that. So these are results that are already well known. And this one now lead to factorizations of the Fock space, gamma L2 R plus, which is equals to, you can factorize it into 2, which is an interesting result by remote 2.3 for above. Okay, so later on we now define what we mean by E, ET, ET, up T. This E is, you can see that we emphasize the emphasis is bold. Bold E, bold E sub T, bold E cap T. So we are defining it as follows. So they are linear spaces generated by the vectors in these Fock spaces. So all of these are Fock spaces. Fock spaces L2 gamma R plus, L2 gamma 0, L2 gamma T0, T infinity, respectively. So that's what the linear spaces generated by these exponential vectors in these places. We have said the other time that E plus dagger, they are subspace of the exponential vector that are dense in the Fock space. So respectively, so we can now put E to be the span of ET, F in L dagger, ET is span of EF, F in L dagger, and E cap T is span of EF, F in L2 dagger infinity. Then we now introduce the following spaces. If we do that, so we are just building our space where quantum stochastic calculus is done. So we are just getting to the space now. So we have one, we call it A equals to the space of all maps from D tensor products, algebraic, that symbol there means algebraic tensor products. D cross E with values in R cross tensor products with the Fock space generated or determined by L2 gamma. Okay, that's our A. You remember how we define L dagger the other time? The set of all map from D cross tensor and algebraic tensor E to that Fock space, that the domain of their action contain D cross E. I hope you are following. So create of E. And then you also note that the Fock space, the codomain there, R cross gamma AT, is also a Fock space. So the tensor products of a Hilbert space and the Fock space is also Hilbert. Okay, the tensor products of the Fock space and Hilbert space is also Hilbert. So AT is denoted by L2 dagger of T. We now put our ET here, dagger O of T cross 1. That cross 1 is saying that you multiply this space. You can multiply tensor with operator 1T, which we have defined before. And then A cap T is just 1T tensor plus the tensor product, algebraic tensor product, ET, gamma R, gamma, R tensor L2 gamma. Okay, so defined by L2 gamma. Where this one, the algebraic tensor denote algebraic tensor product, and 1T respect denote the identity map on. Thank you. Can you hear me now? Can you hear me now?
Yeah,
okay.
Yeah.
Okay, thank you. This the network was going up and down here. Sorry about that. So we are talking about the building of our spaces where our integrand take values. So we have AT and all of that. So I've said the other time that they call it A is a linear space, and so every linear space we can endow with a topology. So we now endow this linear space with a topology, as a result of the Houghton and Porterati fundamental result of 1984. That was what informed our topology. So the definition 215, definition for every eta side in the tensor E, we define this seminum on L tilde on L by the seminum of X with respect to eta psi is just the absolute value of the inner product of eta psi, comma X psi, the absolute value for each X in Collie A. You can see for each X in Collie A, X is an operator that is defined on D cross E with valued in R cross tensor Fock space determined by L2 gamma. So X here is an operator, not just an abnormally number or just so then these collections of seminum is a family of seminums on Collie A theta, and every one of us know that every family of seminum family of seminum every family of seminum generate a locally convex Hausdorff topology. The family of seminum on Collie A topology on L determined by this family. Okay, so notation and that. So we now know, we also know that every locally convex topological space may not necessarily be complete. So we can complete it. We can use its completion. It can be completed. We have theory in the literature that tells us that incomplete locally, topological space, and incomplete topological space can be completed. There's a completion, associated with every locally topological space, every topological space. So in this case, now we have our topological space, the locally convex topological space determined by this family, and then we now use the completion. We now work on the completion. So the completion is what we call, we remember that A of T, okay, let me use the completion. Okay, look at notation 2.16. Notation 2.16. We denote by A tilde, and that as the completion of Collie A, Collie AT, and Collie A cap T. Sorry, so that's the completion with respect to their topology generated by the family of seminum. Okay, so that is now on what we are now working on. So Boston-Fock contour stochastic integration now. So before defining a contour stochastic integral employing what follows, we present a number of important notation. Definition 1, a map X. Look at how we define our stochastic process now. A map X that map I, where I is any set in where output is the positive segment of the real number line. So any map that takes I to L tilde, as we have defined before, is called a stochastic process indexed by I. Look at it now. So the domain of our stochastic process is, the codomain is L tilde. It's defined on I. So any one, unlike the classical Ito stochastic processes, we do not need to talk about some other condition for to be a stochastic process. But in our own form, it is enough that we have a map that takes I to a stochastic process indexed by I. Two, adaptedness. We have the notion of adaptedness. So T belongs to AT, call it tilde. Remember, AT is also locally, complete locally bounded space. Pretty. So if you have x of t for each t in I, you have your x of t in that is a map. You would say that X is adapted. So we do not by add H to the set of all adapted stochastic processes indexed by I. So that is the symbol which we are going to use. So we can show that this space is also a linear space, because every two supervisory process that is that is adapted, their sum is also adapted. So it's a linear space, and then of every adapted stochastic process is also adapted. So we have that. So now we go on to what is called the space of adapted spaces, adapted stochastic processes on A tilde. We say that the member X of A tilde is weakly absolutely continuous if the map T, this map, is absolutely continuous for arbitrary eta psi in D cross E. We denote this set by AD A tilde, weakly, okay, by this set in AD A tilde by add A tilde whack. So we are talking about the set of all weakly absolutely continuous map from T to that, So it's locally P integrable. A member of an adapted stochastic process is locally integrable if the seminum of x of t dot raised to power p is the best measurable. Integrable on tt on every sub interval of I for each t in I. P, a number lie between 0 and infinity, an arbitrary pair eta psi in D cross E. So locally, absolutely, locally in the sense that we are just resisting to a subset of I, T not T. So we denote this subset of adapted processes by LP lock. Locally in the sense that if you take just any subset of I, so it's P integrable over that subset. And this is very important for us as we go on to the theory of integration. We demand all these things. There are so many situations where this locally integrable, P integrable conditions are required. Okay. So another definition, let B of R denote the Banach space of banded endomorphism of gamma, as we said the other time, and let the spaces L gamma log R plus, L infinity B gamma log R plus be defined by this is our definition, so that you understand what we are talking about. L infinity gamma log R plus, just the set of all maps that take R plus to gamma. Remember, gamma is a Hilbert space, or it's a Hilbert space. It's linear, so that F is linear, measurable, and locally bounded function on R plus. Linear, measurable, and locally bounded functions on R plus. Okay, that is what we call L infinity gamma log on R plus. Linear, measurable, and locally bounded function. So measurable in the sense of the fact that the pullback of every open set in gamma is also measurable in R plus. And locally bounded function. Locally bounded means that you can get its constant m, so that the norm of f is less than or equal to m for every subset of R plus. So that's locally bounded. So the other one is L infinity beta gamma L plus local R plus is just the set of pi that map R plus to that matter, so that gamma is linear, measurable, and local. In fact, this is what we use for one of the coefficients. We demand that the coefficient now phi come from L infinity V of gamma log. where B of gamma is just a set of banded endomorphism, which is also Banach. You know that from theory of functional analysis, that is also a Banach space. One gamma is Banach or Hilbert. So for F in L infinity gamma log and phi in that space, we define phi F is also L infinity gamma log by this definition. So let me tell you that this definition arose as a result of the requirement of forcing and posterity for the integral to exist. We cannot talk about differential equation in the sense of Hausen and posterity. Okay, so we now have a Boston contour stochastic integration now. So this is how we come across the integrator now. So also for F in L2 gamma R plus, phi in L infinity B gamma log, we define the operators AF, A dagger F, and lambda in L plus. Look at this one, D to L2 gamma. That is the Fock space determined by L2 gamma as follows. A of H, E of G is equal to that. That is how you define. Where this inner product is the inner product in L2 gamma multiplied by E of G. And then, so that is how it operates. The operator A of F operates this way. A gamma of F operates this way. Lambda phi operates this way. And let me say that A of F, this small A of F, A plus of F, lambda of F, they are quantum, they are field operator, basic field operator associated with quantum field theory. So it is as a result of that we have that. Now, we now come to the capital one. So the operator A of F, A dagger of F, lambda pi for arbitrary F in L infinity, and phi in L infinity, beta gamma log, give rise to the operator valued maps as follows. So we now have this A of F dagger and half phi, defined by what you have here. So defined by what we have here now. So defined by what you have now. Okay? So that is how it is defined. So it's talking about A of ft is just A of the indicator functions of 0 of t. So everybody knows what an indication function of indicator function, characteristic function, you know. So the characteristic function of is 1 if t belongs to that space and 0 if it's outside. So if you now take A of f multiplied by characteristic function, and then you take the other one, A dagger f multiplied by characteristic function, and then lambda multiplied by characteristic function, we now have our capital A of f dagger and half of pi, which are integrators in the sense of Hausen posterity. Whereas can denote the indicator functions of Borel set I. Okay, so that much we have now. That is what we have for now. Maybe we can give some room. Maybe I can start from here tomorrow, because this calculus question now, so that I start from here and then let us see how it works out in terms of quantum equation, in terms of quantum inclusion. Okay. Can we have question now? Can we have question now?
Dr. Bishop.
We have question now. Okay.
Please, people should type their question.
Okay.
People should type their question.
Okay. So let's have the question now. Okay, channel 14.
Mrs. Bishop, you're muting yourself now.
Maybe you should mute Bishop. Sometimes the host has to mute the Bishop. Can Professor Oladiru mute her now?
Hello, sir.
Dr. Bishop, you're already unmuted.
Okay, sir. Thank you so much.
I
hope you can hear me.
Okay.
Thank you so much, Prof, for that brilliant.
Yes, I can hear you now.
Presentation, sir. Thank you so much.
Thank God.
Now we should have our questions.
Okay.
If you have questions, please send it on the chat. So we pick the questions from the chat.
Okay. So do you have question now?
One question said, sir, will the slides be available for us after now?
Yes. We will make it available. That is why I make it so comprehensive so that people can understand it.
Okay, sir.
We'll make it available.
Okay, sir. Thank you so much, sir.
Okay. Okay. Any other question?
There's no question, sir, but I want to ask a question. Can I?
Okay.
Hello, yes, sir. So how do we, how can we make this space, sir, to have some of the properties of a Banach space, maybe by maybe defining a norm and so on? How can we do that?
How can we do what?
How can we impose some properties on this space so that it can function like the Banach space?
Okay, that's a good question. You know, that's a question for further research. But we have the theory of highly convex spaces. You know, the theory of highly convex spaces is what now, and you see that in the LT that we have defined, is a locally convex space that's defined. So to make it a Banach space is another thing entirely, because we need to look at a situation where where the seminorm become norms. You know, the difference between Banach space and the locally convex space is that in the Banach space you have only one norm that generates the topology. But on the locally convex space, you have a family of seminorm. You have a family of seminorm. You know, we have a family of seminorm that we have there. To make the family of seminorm, to impose the conditions on the family of seminorm that will make whatever you have to now behave as if you have a Banach space. As far as I know, it's an open problem that has been done. And you also know that in quantum calculus, whatever topology we impose on A tilde, on calling A, it depends on result that we have already had before. For example, now the results of this weak topology that I started with, you know that we also have some other topology. The result of this weak topology that I started with is as a result of the first fundamental formulas of Haussler and Postrati,
Yes, sir.
Which we are going to deal with later on.
Okay, sir.
Then the second, also, you know, Kagure has also went on to develop some other ones in his paper in 2007. You have about 7 topologies that can be endowed on the calling A, you know. So we have what we call the strong topology, we have what we call the weak one, the star strong, the star weak, depending on the kind of work that you are doing, depending on the kind of results that are available, these are the kind of things that determine the topology that we use on calling A, the space of observable. That space called A is what we call the space of observable, in general. So we have not really got to a situation unless we have results from functional analysis that tells us how to convert a locally convex space to a Banach space or to a Hilbert space. Okay, which we don't have now. I don't think there's anyone that have done that now. So it can be an open problem to Dr. Bishop. Maybe we can just harmonize all this topology in one place. But as of now, we have to do it piecemeal.
Okay. Sir. Thank you so much. Yeah. Let me take some other questions here. Somebody is saying, well done, Prof. I need detailed explanations on Wiener space and Fock space, Hilbert space.
Wiener space?
And Fock space, Wiener space and Fock space, Hilbert space.
And, I said the other time that...
Shall I take...
You said?
Shall I take another question? I said there's another question. Shall I take them one at the time?
No, let me answer that one on the Wiener space.
Okay, sir.
Can you hear me?
Yes, speak on.
Yes, sir.
So what I'm saying now is that the Wiener space is associated with classical calculus, stochastic calculus. So we have the Wiener space. Wiener space is a space where you have the sample space, you have the sigma algebra of members of the sample space, subset of the sample space, and then you have an operator, which is the Wiener's or Brownian motion that acts on that space. So that is why we call it a Wiener space. So Wiener space or Brownian motion is space that is generated by Brownian motion, is there. So, but what we now have, what I said, presented the other time, is to show how you can convert a Wiener space from the classical theory to the equivalent in quantum theory. So, to equivalent in quantum theory, things that are available. You talk about the classical probability spaces. The Wiener space is a classical probability space. And then we also have the quantum equivalent of them, which we also talk about. So what we did was to, when we are talking about realization of the Wiener space from in terms of the quantum calculus, that is what relate to all those, the choice of the alpha and beta, the choice of the Fock space, the choice of the initial space, and all of that I did. So space is still the Wiener space on its own right, the classical theory. But what is the equivalent in quantum theory? And what are the advantages in quantum theory that we have? So these are what we are emphasizing. What are the advantages by reformulating a classical theory in quantum form? So if the person who had the question would sit down and look at this thing, so you have to get interested in the work. You don't be scared by so many symbols or whatever. So there are so many open problems, but one needs to understand the rudiment clearly and know what are the research direction, what are the kind of things that are still open, what have people done before now. And what are the kind of things that need to be in the situation? Okay, question.
Okay, thank you so much.
Can we have more question?
Yeah, another question, sir. This person is saying, can we consider the work on time scale rather than the real line? Did you hear me, sir?
They work on what?
On time scale rather than the real line.
Time scale.
Yes, sir.
Rather than real line.
Yes, sir.
Okay, that may not be impossible. Those are possible research area that we can. So not on real line. But one thing we know is that when the theory of integrations, stochastic integrations, deal to the real number line. So deal with the real number line, and that is why we call it time. You know, you need to know what are the kind of things that happen within the timeline, within the time. Okay, between T naught and capital T, what are the kind of things that happen? You know, so when you have situations, a model that is random, okay, that is stochastic, so we want to know what happened. And as a matter of fact, stochastic phenomena are dynamical system. You know, they are dynamical, that is system that changes with time. System that changes with time, they are dynamical system. Whether you are talking about quantum system, you are talking about stochastic, classical stochastic system, all of them are dynamical system. And when you are talking about dynamical system, you have to associate with the time factor. So maybe what I'm suggesting, one can look at it much more, but there's still much work to be done when it comes to dynamical system generated by quantum calculus, classical stochastic calculus.
Okay, sir. Thank you, sir. Another question says, any relationship of measure space with the space? That's, I think he wants to say with the Fock space. I think he's saying any relationship of measure space with the Fock space.
Any relationship with measure space?
Measure space, with the Fock space.
Okay, well, there are relation. You know what I've said, maybe if you emphasize that one again. You know, when we are talking about classical processes, so classical stupidity, we have what we call a measure space. When we talk about classical measure spaces. So what is a measure space? You have a space consisting of a non-empty set, omega, associated with sigma algebra, and then the next one is a measure. So measure a set theoretic function. A measure is a set theoretic function that is defined on the sigma algebra in such a way that every pairwise disjoint sequence from the sigma algebra, you take the measure on the union, will give you the sum of their measure. So, and we know that in classical probability space theory, the probability theory, probability function is also a measure of, so that is the classical arena. Now, when we are now talking about quantum arena, there are transition, from the classical arena. It's not the subject of this workshop, but we have a situation where in the classical space, what is the equivalent in the quantum probability? So we have two probabilities now, the classical and the quantum, the classical and the quantum. So we have the classical structure of probability as a result of probability space and probability theory, classical probability theory, and then we also have the quantum structure as a result of quantum probability theory. So two of them, they are theories that go in parallel. One is a generalization of the other, and that is why we are saying that they are associated. They are associated, and that they're associated with themselves. So there is an association between measure space and the quantum space. So there are so many references in the literature where somebody can pick it up. Association, what are the associated spaces to calculus? One of our colleagues did a PhD in that area many years ago. Dr. Malik, it was his own work was on the associated quantum space. When you have the classical spaces, what are the associated quantum spaces? Associated. So you now transition from major theory to quantum theory, which is operator theoretic. Okay. Any other question?
Sir. Thank you, sir. I think I will take this as the last question because the next speaker is getting set to present, sir. So
Okay.
Somebody asked also, how related is this to Hilbert space? So how can we relate it to Hilbert space?
How can we?
He said, how can we relate it to Hilbert space?
Which one? Which Hilbert space?
That's what the person wrote. He said,
We have
how
already
related to Hilbert space?
We have already talked. Maybe it's not following what you are saying. So Hilbert spaces, when we talk about space, a Fock space is a Hilbert space. A Fock space is a Hilbert. When you have a tensor product of a Hilbert space with a Fock space, you get another Fock space. And that is the domain where the observable, the quantum observable, that is quantum processes, quantum random variable take values. They take value there. So Hilbert spaces are involved all along in quantum theory. But in the classical theory, in the classical probability theory, we have so many other structures there. And of course, we have LP spaces in the classical theory, of which L2 is Hilbert. L2 spaces are well known to be Hilbert. So LP spaces, generally, they are Banach, the factor, but they are not Hilbert. But it's only L2 that is Hilbert. But when you come to quantum arena, we deal with Fock space a lot. Especially in the Hudson and Topology theory. I said the other time that there's a theory of quantum integration, but our own focus here is on integration developed by Hudson and Topology in 1984, which dwell extensively on the applications of Fock space, which are Hilbert spaces.